Keith Berns here from Green Cover Seed, talking about Carbonomics and healthy soils and what that all means. Keith is the co-founder of Green Cover Seed based in Bladen, Nebraska. Their mission is to help farmers and ranchers regenerate God's creation for future generations. We will have a Q&A section at the end, and we also have a survey after the presentation is over that we ask you to fill out that will automatically take you to. So without further ado, I'm going to let Keith get started on his presentation here.
Okay. Can you see my presentation there okay, Eric?
Yes.
Okay, great. Well, good to be here this evening, folks. I haven't done any presentations for a while. COVID is kind of taking me out of my normal routine. I typically do quite a bit of speaking around the country, and so it's nice to be able to speak and not have to travel. So glad to be able to share with you folks tonight. So tonight I want to talk about Carbonomics, the wonderful economy of the soil. But first, just a little bit of background. We've been farming here in south central Nebraska, Bladen, Nebraska to be exact, for over 30 years. We've been no-tilling here for 30 years. My family's been farming here for over 100 years. We're about half dry land and half irrigated, corn, beans, and a cereal rotation. And since we've kind of started down the soil health path, we've added things like rye and triticale and oats and barley and vetch and sunflowers and buckwheat to the crops that we grow. We've been doing cover crops now for 11 years. I need to update my slide. We've been doing it for 11 years. We started Green Cover Seed in 2009, and you can see on the screen here, this is an aerial shot of our facility. Everything here has been built since 2011, and that just gives you an indication of how fast things have grown. One of the great things about the company that we have and the connections that we've made is that we get to be in a lot of things. If you haven't watched this video called The Living Soil, I would really encourage you to do so. Just go to livingsoilfilm.com. It's a great, about an hour-long movie about soil, and they film farmers from all across the country. And they came out to our farm. They wanted to have us be a part of this. And I just want to show you a little clip of it because it kind of sums up farming, I think, a little bit. But I would encourage you to watch this movie if you haven't. And so I just want to show you this little clip here. The movie crew came out. Let's see if we can get it to play here. Nope. Hold on. Well, we may not get this part to work. If we get time at the end, I'll tell you a little bit more about that. So anyway, what I want to do this evening is compare one of the most complicated systems in the world, and that's what's going on in the soil. It is really very complicated, as you'll see. I want to try to share a little bit more about that by comparing it to something that we understand inherently because we live in it every day, and that's the economy of a country. And so if you look at the 7 keys to a healthy economy, we're going to see that these same things apply to a healthy soil. So we've got things like supply and demand and currency and capital, energy and resources, infrastructure, defense and protection are all keys to an economy, but they're also keys to a healthy soil. And so we're going to go through each one of these and show exactly how each one of those plays into a healthy soil and having a profitable farming operation. So first of all, the first thing to understand is that the soil economy is based on the sun. Solar energy, really as farmers, what we do is we're capturing solar energy and we're turning it into something that we can sell, something of value. And so that's the basis of the economy. But then the 3 main players within this economy that farmers are concerned about all the time, of course, we have the soil, and then we have the plants that are growing there. And the third part of this economy that a lot of times gets ignored, and that's the animals or the biology. And I'm not going to spend a lot of time tonight talking about the large animals like the cattle, but we're going to spend quite a bit of time talking about the little guys, everything from earthworms to fungi to bacteria, because they play a very, very critical role in this economy in making things work the way that they are created to work. So just going to go through these different economic principles and show you how they apply to the soil. So first of all, on the supply side, that's the first part of an economy, is you have to supply something. You have to produce or manufacture something. And so in this economy, plants are supplying or producing carbon. Okay, this is photosynthesis. CO2 plus H2O equals C6H12O6, which is a glucose carbohydrate sugar, and oxygen. Oxygen is just a byproduct, but it's very important for all of us who like to breathe. But this glucose molecule right here, that's the carbon that's going to drive the whole system. And so with photosynthesis, we're taking CO2, which is kind of a waste product. In fact, you know, I think in the very near future, farmers are going to get paid to take this out of the atmosphere. But that's what plants eat. That's plant food plus water. And it requires the energy of the sun and then the magic of the chlorophyll in the cell walls of the plant, the chlorophyll. It turns these two products into glucose and oxygen. So that's what the plants are supplying. The soil is providing nutrients through the minerals. So if you look at this little chart over here, just ignore nitrogen right now. That's one of the things that plants need in large amounts. That does not come from the soil. We'll talk about nitrogen later. But potassium and phosphorus and sulfur and calcium and magnesium and iron and manganese and boron, copper and zinc, these are all minerals that are coming out of our soils. They're naturally occurring in our soils. They're part of the parent material. And that's what the soil is providing for this economy. Now, the soil also provides a habitat for roots and for the biology. It gives them a place to live. It's their habitat. It's where they can grow and thrive. And it also provides water storage, which is very, very important, especially in dryland situations where we can't have the ability to irrigate. When we get a big rain, we have to catch it all and we have to be able to store it all because we don't know when the next rain is coming. So soil is that big sponge that holds all of our water as well. And then lastly, the biology, they have very, very important roles to play. They are producing nutrients through fixation. And again, we'll look at that in more detail here in a little bit. But they're also making things available. They're cycling the nutrients. They're really what's driving that whole nutrient cycle. They're also providing some very critical roles in defense and protection, defending the plant, protecting the plant against diseases and insects. And we'll look at how that whole thing works as well. And then on the demand side, because you can have supply, but you also have to have demand. You have to have someone that wants to buy what you're producing and to make a good economy. Plants need nutrients. Plants need water. We all know that. But they also need to be supported with protection and keeping them healthy. And we'll look at how the system provides that to the plants. Soil needs carbon. On the demand side, soil has to have carbon. If the soil doesn't have carbon, it is not going to function properly. It is not going to grow very good crops, and it's going to require very high inputs to do it. But it also needs services. Soil can do a lot of things. It cannot protect itself. And if the soil is exposed, if you can walk out in your field and see the soil, then it's subject to being washed away and blown away. So the goal that we have on our farm is we never want to see our soil unless we go out and specifically look for it, dig down, move all that residue aside and look for it. And that's because if we can't see it, then we know it's well protected. And then the biology, they have very simple needs. They need food and they need habitat. You give them that and they're willing to work and they'll do some pretty cool things for you and they do it really cheaply. So in a strong human economy, one of the leading indicators that we have a really strong economy is a low unemployment rate. And 7 months ago, I could say, just look at our economy right now. We have a very low unemployment rate. We have a very strong, robust economy. Well, we all know what the last 7 months has done, what COVID has done in wrecking the economy. So we no longer have a low unemployment rate, and we have a lot of people who aren't able to contribute to the economy like they would like to. And so our economy is not as strong as it should be, or was, or will be again. And so it's the same way in the soil. If we want to have the strongest economy as possible, we have to have all of the entities producing and consuming and contributing, and diversity is very important. We don't want just one thing contributing. We want multiple things. So we don't want just earthworms. We want bacteria and fungi and protozoa and all these different things contributing to the economy of the soil. But here's what happens. This is what happens when we farm. And I can say this because I'm a farmer, and this happens to us. We do this. We provide something that I call agricultural welfare. If we're going to talk about this in the terms of an economy, we have to talk about welfare. And welfare is simply when you give something to somebody And we do that all the time to our crops. When we externally provide the plant with everything that it needs from the outside, we really weaken the economy. And the two main things that we provide are the fertility inputs, the synthetic fertilizers, and crop protection inputs, different types of pesticides. And when we supply all of that to the plant, we're essentially taking jobs away from other members of the economy that are supposed to be doing those. But for whatever reason, they are now unemployed and they can no longer do it. So we have to give our plants and our soil these handouts. Now, that's not always the wrong thing to do. I really like what Abraham Lincoln says about this, not about the soil, but about the human condition. He says, you cannot help men permanently by doing for them what they could and should do for themselves. And I really like that, because when it comes to helping people, we absolutely need to help and we should help. But he says we're not going to help them permanently if we continue to do for them what they could and should do for themselves. And it's the same way with our soil. It's the same way with our crops. We need to help them out when they need it. But if we continue to do that, they're never going to get to that state, the natural state where they should be, where they're doing a lot of this within the economy itself. So we need to allow the system to work the way that God created it to work. And that's having the soil and the plants and the biology all working together, each one contributing a major share to the economy. So we talked about supply and we talked about demand. Now currency is the third part of a economic structure, and currency is very important because it allows goods and services to be exchanged more efficiently between the buyers and between the sellers. If you don't have standardized currency, you're not able to make these transactions very efficiently. And in our soil system, we have the perfect currency, and that currency is carbon. Okay, carbon is the currency that drives this whole system. So here's photosynthesis again. CO2 plus the H2O is making this glucose molecule, C6H12O6, and oxygen. So this sugar molecule right here, this carbon right here, this becomes the currency that drives the whole system. So when you say money doesn't grow on trees, that's not true for this economy with the plants and the soil. It literally does grow on trees and on corn plants and soybean plants and wheat plants, because we're literally printing our own money for this economy, because we're only limited in how much of this glucose molecule we can make. The only thing that limits it is how many plants we have growing and how long they grow. And so we can actually produce more carbon and put more carbon into the soil simply by having more plants growing more of the time. Let's look at how this works. The plants are growing, and through photosynthesis, it's making that carbon molecule, that C6H12O6. But here's the thing, it doesn't stay in that form. That carbon molecule is stripped off that glucose, and it's recombined inside that plant into many, many different carbon compounds. And then what the plant does, it uses some of those to grow, but the experts tell us as much as 40 to 50% of the carbon that a plant makes through photosynthesis is not used for the plant to grow. It's not used to grow new leaves or new roots or new plant tissue. It's actually leaked out through the root system, and I've got a really cool picture later on that shows you this happening, but it's leaked out through the root system into the soil in the form of these root exudates, and the biology, that's what they eat. That's their food source. So they're right around what we call the rhizosphere, and that's where the roots are in the ground. So you have all this biology, and they're eating, they're consuming those carbon root exudates. That's their food source. But just like in the human economy, there's no such thing as a free lunch. You have to pay if you want to play. And so the plants are really quite smart. They're quite intelligent, because if they're not getting a return for their investment, they're going to stop putting those root exudates out there. So if there's no biology around to consume those root exudates, the plants will severely limit how much they are putting into the soil. But if there's lots of biology, that plant's going to pump out a lot of carbon into the soil. And so what the bugs do, the biology does, in exchange for the carbon that they're consuming, they're providing the plant with services such as sourcing nutrients and delivering nutrients and protecting the plants. And so this is the basis of the economy right here. The currency is the carbon, the payment is made to the biology, and in return, the biology provides these services back to the plants. Carbon is so very critical, really, to all of life. You and I are 19% carbon. Carbon can form over 10 million different chemical compounds. It's the most versatile compound out there. It's the most important but the most overlooked of all plant nutrients. Most farmers never think about, do I have enough carbon out there for my crops? but it is the most used and the most important part of any plant. It's the main food source for soil biology also. That's why it's so important. When we have extra carbon in the soil, it helps normalize our soil pH. In other words, if it's too high or too low, more carbon in there can help bring it down to the middle. It increases the cation's exchange capacity. It increases the availability of all these important nutrients, and it reduces the availability of things like sodium and aluminum that can build up to toxic levels. And it's the perfect currency because it can be collected through photosynthesis, just like regular currency can. You can spend it, and the plants do that when they trade it to the soil organisms in exchange for those services. It can be saved, and we're going to look at that next, in the form of soil organic matter. And it's desired by all members of the economy. You have to have everybody in the economy buying off on having the currency that everybody agrees on. It also has different states, just like our currency. You have the gaseous form of carbon, which is CO2. You have the liquid form of carbon, which is moving up and down in the plants and through the soil. And then, of course, we have solid carbon, which is fixed in the tissue of all living organisms and in the organic matter. And again, the experts will tell us that carbon can move these states very, very quickly. It can be just a matter of minutes for a plant to take CO2 out of the atmosphere, convert it into a liquid type carbon through photosynthesis, move it down through the plant into the roots and out through the roots into the soil. It gets consumed by an organism and converted into solid carbon inside that organism's body. So carbon is very, very versatile, very, very flexible. It drives the whole system. It literally is the cash that drives the whole system. And then when we have excess currency, when we have excess carbon, we can accumulate that, we can store it, we can save it, and that's called capital. So in our economy, we have capital, and that's money that you have in the bank. It's equipment that you bought. It's assets that you own. Now, sometimes capital is borrowed, hopefully paid back, but it's borrowed capital sometimes. But having access to capital allows you to grow, and it's the same way in our soils. The capital of our soil is going to be the soil organic matter. And we could spend a week just talking about how important the soil organic matter is. In fact, here was a whole presentation done by Dr. Jennifer Moore-Kuchera with NRCS, and she was talking about the benefits of soil organic matter and how it is linked to all of these things with soil health. It is the most important thing to know about your soil. How much organic matter do you have? Because it's a measurement of how much carbon do you have. It's that long-term stored carbon. And what we see is high organic matter soils are just like capital-rich economies. Now, the United States has, I think, arguably the strongest economy in the world. We're not as strong as we used to be, but we'll get there again. But one of the reasons is that we had access to lots of capital, and that made us productive, and it made us stable and resilient and efficient. And it's the same way in our soils. When we have soils that have higher organic matter levels, they're going to be more productive, more stable, more resilient, and more efficient. They're going to be the most profitable soils that a farmer can farm. And because it just does that much for helping to produce crops. Now, you can't increase your savings account unless you have an excess of cash income. If you aren't earning more than you spend, you cannot increase your savings account. And it's the exact same way in the soils. We can't increase our soil carbon currency, or that organic matter. We can't increase it unless we're bringing more carbon into the system than what we're getting rid of. Now, how do we lose carbon out of a farming system? Well, there's a couple of main ways. One way is you haul things off that you harvest. So if I'm planting corn and I harvest 200 bushel corn and I put that in a semi and I haul it away, I am removing a lot of carbon from that system. That's a carbon leak out of the system. So I have to have more carbon put back into the system than what I've taken away. Otherwise, my organic matter levels are going to go down. And that's essentially what's happened for the last 150 years of farming. We've removed more carbon than what we put in. And so our organic matter levels are going down and down and down. And some of that carbon ends up in the atmosphere as CO2, and we need to put it back into the soil. And the other way that carbon is lost from the soil is anytime we do any kind of soil disturbance, particularly tillage, it stirs it up and it introduces oxygen into the soil. And when that oxygen and that carbon get introduced, guess what? It turns to CO2, carbon dioxide, and that floats away into the atmosphere. So we lose carbon at a much, much higher rate when we do heavy intensive tillage in our systems than when we're doing a no-till type system. So we can't increase our carbon in our soils unless we have more carbon in than what we have going out. And in most farming systems, that's almost impossible to do unless we're using cover crops. And that's why, if you've heard much about soil health, you probably heard a lot of talk about cover crops. Well, the power of the cover crop is that it's growing in a time frame when other plants aren't, and it's putting carbon into the soil. And because we don't harvest the cover crops, that carbon stays there. It's a net carbon gain. And so once we introduce cover crops into our farming system, we have a much better chance and a much quicker chance of increasing the soil organic matter and really improving the system. Okay, so moving on, energy and resources is the next sector or segment of the economy. We get our economies energy from the sun. We talked about that, solar energy. It drives and it powers this process, this manufacturing process, if you will, that's turning CO2 into glucose. It's powered by the energy of the sun. And so all we have to do in farming to really start doing some pretty good things is put out solar collectors. And fortunately for us as farmers, we don't have to spend the money on these man-made solar collectors. All we have to do is plant seeds. You plant a seed, up comes a plant, and out pop these green solar collectors called leaves. These will start absorbing solar energy, and they turn it into chemical energy in the form of that glucose molecule, which then becomes other products within the plant. And so when we aren't having plants out there collecting solar energy, we're really wasting opportunities. We're really wasting the solar energy, and it's hitting the ground, and it's making the ground hot, and it's making the ground hard, and it's evaporating our water. So really a lot of bad things happen when sunlight hits the ground. We want the sunlight to always be intercepted by a green plant as much as possible. And a healthy soil economy should not need significant purchased energy inputs. And I can say that because our prairie soils that we farm here were built over thousands of years with these tall and short grass and mixed grass prairies, and there was no outside energy input. It was just the system working the way that God created it to, and it created these deep, rich, wonderful soils. Now, we can't really probably ever go back to a zero energy input system, because if we are pulling something out of there, we're harvesting a crop, we're taking away hay, or we run cattle on the land, there's going to be some energy loss there, and it's going to have to be put back in. So the goal here is not to completely eliminate or reduce all this, or not to eliminate it, but we want to reduce it as much as possible. And when we look at our farm, when we look at the energy budget of a farm, the number one energy use on a farm, it's not natural gas, it's not diesel fuel or gasoline or propane. The number one energy use on a farm is nitrogen fertilizer. And I'm going to show you why that is here next. So on the resources side, the resources that are needed in manufacturing and making this economy work, the number one thing is carbon. We talked a lot about carbon already. And essentially our carbon is free. We get all the carbon that we need for our crops out of the atmosphere through CO2. And like I said, I think someday, some people are already doing it, but it's going to become more widespread, where farmers can actually sell carbon credits for removing excess carbon out of the atmosphere and putting it back into the soil, and essentially sequestering it and taking it out of circulation and putting it into long-term savings in the soil. And so our carbon is free. Our nitrogen is not. The number two thing that plants need is nitrogen. And I want you to look at this graph. This is really interesting. This is a pie chart of the atmosphere. So everything added up is 100% of the atmosphere. This tiny little pink sliver at the very top, you can't even probably see it very well, but that is the carbon dioxide. It's about 0.04% of our atmosphere, not 4%, but not 0.4%, but 4/100ths of 1%. Okay, that's a really, really small number. 4/100ths of 1% of our atmosphere is carbon dioxide. Okay, very, very small amount. But yet we can grow 300 bushel corn, and we can grow 80 bushel soybeans. We can grow all these wonderful crops. And essentially, we're pulling all the carbon that they need out of that little fraction, out of that little sliver of the atmosphere. Plants are pretty spectacular when it comes to being able to do that. They can extract that CO2 and put it into the plants. Now, the big blue part of the pie, 78% of our atmosphere is nitrogen. Okay, so don't miss the point here. We pay zero for this amount of carbon. That's all free, but we have this much nitrogen in the atmosphere, and as farmers, we literally spend billions of dollars every year to put nitrogen into our crops. Okay, even though we've got all of this in the atmosphere. And you go, well, why is that? That doesn't seem right. Well, there's a good reason for it. And there's good news and there's bad news when it comes to this. The good news is that nitrogen in the atmosphere is held as dinitrogen. It's two nitrogen molecules, and they're bonded together with three sets of very, very strong covalent bonds. And so the nitrogen is bonded to each other, and it literally renders it inert. So atmospheric nitrogen is N2, okay, two nitrogen molecules bonded together. It does not want to attach to anything else. And the good news is that we're not dead. Because if you've ever had a whiff of anhydrous ammonia or even Clorox, which is ammonia, that is nitrogen that is not bonded to each other. That is some other form of nitrogen. It's very reactive. It's very volatile. It's very harmful to the human body. And if our atmospheric nitrogen was not dinitrogen, we would all be dead, and it really wouldn't matter. But because it is dinitrogen, we can breathe it in. Every time I take a breath, 78% nitrogen, it goes right back out. It affects me not one single bit. Now, the bad news is it is doing the same thing to a plant. When a plant is pulling in atmosphere to strip off that carbon molecule, the carbon dioxide, it releases the oxygen, it keeps the carbon. It's pulling in 78% nitrogen when it does that. But that plant can do absolutely nothing with that nitrogen molecule. It takes it in, it has to spit it right back out because it cannot get it to bond with anything. Because in order for that nitrogen to have any kind of effect on something, you have to first of all pull those two nitrogen molecules apart, and then you can start attaching them to other things and make them useful. And so if we're going to put it into a plant available form, we have to pull it apart. We combine it with hydrogen or oxygen, and we can make ammonium and ammonia and different forms like that. But it takes a lot of energy to do that because these N2 molecules are very, very strongly tied together. And so a little over 100 years ago, there were a couple of German scientists, one named Haber and one named Bosch, and they came up with a process to be able to pull that nitrogen molecule apart. And it's still in use today. It's called the Haber-Bosch method. And it grew into a big industry, and you can see this is a nitrogen producing factory right here where they're actually they're pulling those nitrogen molecules apart. And the first use of this is in making bombs. Nitrogen, when you pull it apart, is very volatile. It's very explosive. Some of you may remember, I think it was 26 years ago now, the Oklahoma City federal building bombings. Timothy McVeigh blew those buildings up. And what was his bomb? It was a truck full of ammonium nitrate fertilizer. But that nitrogen molecule was pulled apart, and so it had a huge amount of potential energy, and he made a huge bomb out of it. And so we can do that, but it's very, very expensive, and that's why farmers pay billions of dollars every year to put nitrogen on the soil. We're not paying for the nitrogen. There is, get this number, there's 30,000 tons of nitrogen, 30,000 tons of nitrogen above every acre of cropland in the world. There's an infinite amount of nitrogen. The plants can get absolutely none of it. So it has to go through this process in order to make it available to the plant. So that's why farmers spend tons and tons of money on nitrogen. But guess what? What it takes man, these big factories and billions of dollars to do, God created these tiny little bacteria that do the exact same thing at this microscopic scale. So there is an organism called Rhizobia bacteria, and they colonize the roots of legume plants. And so don't ever let somebody tell you that a legume plant makes its own nitrogen, because it can't. Plants can do nothing with that atmospheric nitrogen, but bacteria can. Bacteria can. And so these tiny little Rhizobia bacteria, they can actually pull that nitrogen molecule apart, and they combine it with hydrogen and oxygen and put it into a form that plants can now use. And then the plant is actually willing to pay for that nitrogen, okay? Because as cool as rhizobia bacteria are, and their superpower is pulling dinitrogen apart and making plant available nitrogen, they can't eat that. They can't survive on that. Their food source is carbon, and they have no ability to pull carbon out of the atmosphere. That's the plant superpower. And so the only way these organisms function properly is when they get together into a symbiotic relationship. And so you can see this is the roots of a soybean plant here, and all of these little brown things are nodules. And what that is, here's a close-up of it over here, and one's even cut open. It's all pink. That's the nitrogen that these bacteria, and there's literally trillions of bacteria involved in this one little nodule right here. They're very, very tiny. They're doing this at a microscopic level, but they get together, they form these colonies, and they're very powerful and very efficient at producing this nitrogen that this plant needs. And so that is limited to legume plants, and each legume plant has a little bit different type of rhizobia bacteria that will colonize it and will make those associations. Now, here's some more good news. It's not limited just to rhizobia and just to legumes, because there's other critters out there like azospirillum and azotobacter, and they're discovering new ones all the time. These are other types of bacterial organisms that can do that same thing. They're pulling that dinitrogen molecule apart, and they're making it available to the plants. And these guys, they can give their nitrogen to a corn plant. They can give their nitrogen to a wheat plant. It doesn't have to be a legume. And so this is really good news. And you might be thinking, well, why don't farmers just dump a bunch of these bugs out there and not have to worry about putting all that fertilizer out for the corn? And that's a great question. And the answer to that, I'll go back to this slide for a second. On soybeans require vast amounts of nitrogen to make a crop. If I'm making 70 bushel soybeans, it takes 350 pounds of nitrogen to produce 70 bushel soybeans. No farmer would ever grow soybeans if they had to put 350 pounds of nitrogen on. But this rhizobia can make 300 to 400 pounds of nitrogen in 2 to 3 months, which is a huge, vast amount of nitrogen. And it can crank that out in a couple of months in order to grow these great crops of soybeans. Very powerful. These guys, not so much. They're going to make 30 or 40 pounds of nitrogen in a year. Okay, so that's not going to be enough to grow a full-blown corn crop, but what it is enough to do, it's enough to really give a lot of benefit to a cover crop or to a grazing crop or a perennial crop. And think about it. Have you ever driven along the highway or the interstate and you look out in the ditch or in the median? Do those grass plants ever look like they're nitrogen deficient? Do they ever look lime green or pale green? No, they may look drought stressed or something like that, but you never see those plants look nitrogen deficient. And I don't think the highway department is out there fertilizing them at night when we're not looking. Pretty sure that doesn't happen. It's these guys right there that are in that system, and those plants only need 30 or 40 pounds of nitrogen per year because nobody's hauling that stuff away. It's more of a closed loop system, and that's sufficient to do that. So again, I'm not suggesting that this is going to replace all commercial fertilizer, but it can certainly supplement it. And when we have these as part of our system, it can help other parts of our system a lot. But the only way it does this is it has to associate with a plant, and that's not going to happen unless that plant is willing to pay for these services. And it's also not going to happen if we have excess nitrogen in the soil. Because again, plants are pretty smart. They're not going to give away something if they can get it for free. Okay, the other resource I want to talk about is all these other minerals. So we've got carbon, we've got nitrogen, and then there's all these other things. We've got phosphorus and potassium and calcium and magnesium. I told you earlier that these are all found in the soil. Our soils are made up of these minerals. But again, the plants can't access them. It has to get freed up, or it has to get mined out of the soil to be made available to the plant. So as farmers, what we need to do is hire all these tiny little miners to extract these nutrients from the soil. So there's a really good article in Scientific American a few years ago. It's called Mycorrhiza Fungi Run the Largest Mining Operation in the World. And that's a great title for an article. And so this picture right here is out of this article, and this is a highly magnified piece of feldspar. So just think of this as a little tiny grain of sand, and you can see these little brown channels or tunnels cut into here, and that's literally open space that has been hollowed out. That's literally mine shafts within this rock, this little piece of sand. And this is from an organism called mycorrhiza fungi, and they produce the right chemicals that it can actually dissolve solid rock. Solid stone can be dissolved, liquefied, if you will, turned into liquid minerals, and then that mycorrhiza will give that or sell that to the plant in exchange for carbon. Because as cool as mycorrhiza are, they can't eat these liquid minerals. They can't subsist on them. They have to have carbon from that plant. Here's what it looks like. This is a plant root. These little black circles are what's called an arbuscle, or the headquarters of the fungi. And then the hyphae grow out through the cell wall of this plant root, and they grow out and they explore the surroundings, and they pull in these different nutrients. The author of this article basically says that these mycorrhiza are mining the soil for basic things like the phosphorus, but it's also the hard to come by things, zinc, copper, manganese, which plants need. And here's what she says. I love this. She says, oddly enough, many soils are rich in important nutrients, but they're often locked up in a physical form, which makes them unavailable to most plants. And she's exactly right. Most of our soils have thousands and thousands of years worth of the nutrients needed to grow crops, but yet we fertilize almost every year because our plants cannot get to those minerals in the soil. They have to go through a bug first. They have to go through the biology in order to get there. Okay, the next economic principle is infrastructure, and that's simply the basic equipment and structures that are needed for a country to function properly. And so the two most important infrastructures that we talk about in our soil is transportation and communication. We know these are important because in times of war, it's what you attack first. You try to destroy your enemy's infrastructure, communication and transportation. And if you can do that, you literally will bring a country to its knees. So as I was thinking about this and thinking about the United States economy, I thought about transportation and how we're very blessed with a great transportation system. And we have the interstate highway systems. These are big roads that can move large amounts of goods and services across the country very, very quickly and very fast. But some of us, like I live right down here in the bottom of Nebraska, almost on the Kansas line, it's about 50 miles for me to get up to Interstate 80. It's about 70 or 80 miles to get down to Interstate 70 down here. So I can't take advantage of the interstate system unless I can get there. So what really makes our transportation infrastructure so valuable is all of the highways that go along and tie it all together. And so now there are very few people that live very far from a pretty good highway that will take them to a really good interstate to help move goods and services back and forth across our country. And it's the same thing going on in our soil. These are some very famous pictures of mycorrhizal, that same organism that we looked at earlier. This is a plant with no mycorrhiza. It's just the plant roots. And think of this as the interstate highway systems. These are big roads. These are large conduits. It can move large amounts of goods and services up and down and to the plant, down to the roots, from the soil up. It's taking the liquid carbon down. It's bringing water and nutrients up. So these are the interstate highway systems, which are great. But if there's a piece of nutrient over here, if it can't get to the highway, to the interstate, then it's not accessible. And so what the plant needs is it needs the highways and it needs the county roads to lead to it. And that's exactly what mycorrhiza do. Mycorrhiza grow from these main plant roots. They grow out into the soil and they branch out. They form these hyphal networks. And now there are pathways for water and for nutrients to get to this plant. And there's many, many more pathways for this plant to now, remember the liquid carbon root exudates that's feeding all the biology. It's the plant is pushing it down through here, and that liquid carbon is actually going out through the mycorrhiza and into the surrounding soil, feeding the biology and actually raising up its own workers. Here's another picture of what it looks like. This is another plant root under high magnification. The arbuscle here, and you can see all these little fine filaments. That's the hyphae growing out from that root, and it's going out into the soil to explore and to mine and to extract and to bring those things back to the plant. And it brings in all these things, nitrogen and potassium. But phosphorus is one of the hardest things for plants to get from the soil. It's one of the things that mycorrhiza do best and bring in phosphorus. And mycorrhiza in dry times, they even help transport and supply water to the plant. So it makes a crop much more drought efficient when you have mycorrhiza in the soil. Now, there are other things that are helping transport as well. Earthworms are wonderful. When you have a soil that has a good, healthy earthworm population, you know that your soil is well on the way to becoming healthy, because unhealthy soil, you will find very few earthworms. And when you start seeing earthworms, you know you're starting to do something right. And so earthworms help transport water, because these holes, you can see these holes in this piece of soil, these holes go all the way up to the surface. And when we get a big rain, those are huge aqueducts for bringing water from the surface down into the soil where it can be stored. And when we don't have these worm channels, or we've destroyed them through tillage, those are no longer portals to get water into our soil. So huge help for water infiltration, but they also help bring oxygen down into the soil, surface carbon, and they can also help distribute other biology throughout the soil system as well. And then the other piece of infrastructure that we need to talk about is communication, because if you think about it, how does the plant communicate to the mycorrhiza what it needs? Because if the mycorrhiza is capable of bringing all these different things to the plant, and the plant is very sensitive to some of these things, so take boron, for example. Plants need boron in order to be healthy and to function properly, but they need it in very, very small amounts. And so if the mycorrhiza was bringing too much boron to the plant, they would actually kill that plant from boron toxicity. So somehow they have to communicate what the needs are so that the mycorrhiza and the other organisms know what the plant is wanting. And the way the plant does that is by the different liquid carbon root exudates. Remember I said that carbon can form 10 million different compounds? Well, here's just a few of them: tryptophan and adenine and methanone and palmitic acid and biochainine. And these are just different flavonoids and amino acids, and their lipids and their oils. Each one of these things is communicating to a different organism, and it's communicating different things that the plant is wanting. And here's what it looks like. This is that picture that I was telling you about earlier. This is one of the most incredible pictures I've ever seen. And let me explain to you what it is here so that you can kind of understand this. So this is first of all, this was taken by my friend Jimmy Emmons from Oklahoma. He actually took this picture on his iPhone. He had a little microscope attachment to his iPhone called a Proscope, and he dug some soil up out in one of his fields, and it was where he had cereal rye growing as a cover crop. And he dug this up, and he was able to take this picture. And what this is not mycorrhiza. This is a plant root. So the big white thing is the cereal rye root. And what you see coming off of it here, these are little root hairs coming off the side. But what's stunning on this is look at all the little droplets. You can see them gleaming and glistening here in the light. All these little droplets of liquid that are on these little root hairs. And that's not water from the soil. That's the liquid carbon root exudates that plant is pushing out into the soil to feed the biology. And here's the incredible thing. This is why you never see a picture like this, because when you pull a plant root up, all these little hairs fall off. They're very, very fragile. And if you're really careful and you wash all the soil off, you can preserve some of these root hairs. But in the process of washing it off, all of these liquid carbon droplets all just wash away because they're water soluble and they disappear. And so he was able to get this picture because this piece of this root is not actually growing in the soil. When he dug up that piece of soil and broke it apart, this is a worm channel right here. So the distance that you're seeing from one side to another is the diameter of a worm channel. So, you know what, maybe 1/8 of an inch at the most. And this was growing in the airspace in that worm channel. So it grew in one side of the channel and it grew right out the other side. But it continued to put root hairs on, and it continued to put these liquid carbon root exudates. And so if you think about this, this is 1/8 of an inch of a cereal rye plant. One cereal rye plant will have thousands of yards of roots. You're seeing 1/8 of an inch. One plant will have thousands of yards. And on 1 acre of soil, he'll have over 1 million plants. So when you start doing the math and thinking about how many little droplets of liquid carbon are being pumped out into that soil, it's incredible how much there is. And this is what builds soil faster than anything else, is when you put carbon into the soil through these liquid root exudates. And that's only going to happen when you have plants growing, and it's only going to happen. This plant was highly stimulated because Jimmy is a really good farmer, has good soil health. He had a lot of biology in this system, and so this plant was pumping out as much carbon as it could to feed all of the critters and all the organisms there. pretty cool picture. Another way that plants communicate, they communicate through the root system, through the mycorrhizal fungi. There's been some really good experiments and documentation of how this plant can communicate if it's being attacked by aphids to this plant, and it can communicate by the roots being tied together through the mycorrhiza. It can also communicate through what they call volatile organic compounds, or essentially it's like a perfume. So when you mow your grass, and it has a distinctive smell, and we can sometimes like that. We think, oh man, fresh mown grass, that's a really good smell. Really, that's the plant's defense mechanism saying, I'm under attack, watch out, my neighbor. And it's a volatile organic compound that is released to warn other plants that there's a threat in the neighborhood. There was a really good article in the Scientist magazine that really detailed this in great depth. And it shows how these plants are producing these volatile organic compounds. And not only can they signal other plants, but they can signal predatory insects. So if this plant has aphids and it's being attacked, it will release these certain smells. And then the predators, whether it be a wasp or a ladybug or a spider, different things that would feed on those aphids, the plant will signal them in. And aphids, an aphid infestation can be detected by a ladybug from quite a distance, simply because the ladybug can smell the plant's response to being attacked by aphids. So plants are really smart. They communicate, they cooperate, and they're able to call in an airstrike. But in order to have this, you have to have these predatory insects around. And if you're out there spraying insecticides on everything, you're probably killing these guys as well as the bad things. So the last piece of the economy that I want to talk about is defense and protection, because our soil economy needs to be protected from lots of things. Too much water, too little water, wind, heat, cold, compaction, weeds, insects, diseases. These are all threats to our economy. And so there's several basic things that as a farmer I can do to protect my economy. And the first thing is just keep my soil covered. It's one of the most important things that we can do. My friend Rolf Dirks, who's one of the godfathers of the soil health movement in South America, he says almost all advantages of the no-till system come from the permanent cover of the soil, and only a few of them come from not tilling the soil. We always want to aim at full soil cover. Always keep the soil covered. That's the best defense there is. The second line of defense is plant signaling. We just looked at that in a little bit. I want to show you one more example that really brings this home on the defense and protection side. So this is an experiment done by students at the University of Delaware. They took a house plant, this rock cress house plant, and they infected it with a pathogen called Pseudomonas syringae. And when this plant has this pathogen, it turns the leaves yellow, and then they turn brown. They eventually turn black and fall off, and when all the leaves fall off, the plant is dead. Now, this plant, same plant, rock cress plant, it's infected with the same pathogen, Pseudomonas syringae is in here as well, but it looks perfectly healthy. And the reason that it is because not only does it have Pseudomonas syringae in this pot, but they also inoculated this pot with a beneficial bacteria called Bacillus subtilis. And Bacillus subtilis is a very, very cool bacteria that can explode its populations in a hurry. And so what happens when this plant detects that it's under attack by Pseudomonas syringae, it starts calling for help. And the way that it calls for help is it exudes these liquid carbon root exudates that are signaling Bacillus subtilis that, hey, I'm under attack, come and eat all this good food that I'm going to give you and help protect me. And so what happens is because this plant is willing to feed the bacteria, these bacteria can explode their populations, and this is a highly magnified picture of the root of this plant right here. And all of these little root hairs are surrounded. They've added the color to this. It's not naturally green, but this is a biological film made up of billions and billions of Bacillus subtilis, and they just are coating this plant, and they've actually sealed it off so Pseudomonas syringae can no longer get in, penetrate this root, and make this plant sick. So you've got a plant growing in the presence of a pathogen, but it's completely healthy because the pathogen is offset and it's balanced by the good bacteria. And in natural systems, that's what we see. The good bacteria, the good bugs will typically outweigh the bad ones, and that's why plants can be healthy even though there are pathogens there. Now, another line of defense is when you have healthy plants, they produce these complex compounds which give some natural resistance. This is a really complicated slide. I don't even pretend to understand it all, but basically, this is John Kemp, who has this really good information, basically saying that as a plant turns this simple sugar into more complete proteins and lipids and fats and oils, as they become more complex, insects cannot digest complex compounds. They love these simple sugars. Glucose, they have a ball on that. Once you start turning it into lipids and proteins and fats and oils, insects can't digest that. It'll give them a gut ache. They're not able to do that. They will actually fly off and find another plant that's not as healthy, and you will always see far more insect infestation in unhealthy plants than you see in healthy ones. And so growing healthy plants comes from healthy soil, and it's a circle of health because that just leads to healthier and healthier plants. A fourth line of defense is having these symbiotic relationships. This is another type of fungus that can grow inside of a plant. It's called an endophyte. An endophyte fungus lives completely inside the plant root. This is not going out into the soil, but this fungus is taking carbon from the plant in order to live, and in exchange, it's giving this plant protection from disease, and it makes it more drought tolerant. So this is a picture from the Noble Research Institute because they're doing research on trying to develop better funguses that will infect some of these plants to make them healthier and stronger and better. And then the last type of defense is just have lots of diversity. Most of our agricultural systems have lost so much of the diversity that we used to have. And now when a predator comes in, it can attack one thing because the whole field is one thing. But when we have lots of different things out there, predators can't attack them all. And again, I understand that we have to grow monoculture, corn and soybeans and wheat, things like that in order to harvest the crops. I understand that. But when we do a cover crop, when we're able to get the cover crop into the system, we want as much diversity as possible because diversity means resilience and resilience means protection. So there's the keys to a healthy soil economy. I know there was a lot of information. I just want to kind of sum it up. I've got 8 quick takeaway points, and then we'll see if we have time for just a few questions. Economies are intricately connected, interconnected, and interdependent, and you can't change one thing within this economy without affecting the other. So when we take the biology out of the system, we're going to dramatically and drastically affect the soil and the plants. And when we do that, we have to give all this welfare to the system to protect and save our plants. So the goal of us as a farmer should be to reduce the amount of welfare that we're giving our economy, get everyone working the way that God created them to work, mainly put the biology back into the system however we can, get them working. When we do that, we can increase our cash flow of carbon currency. When we're only growing corn and soybeans, we're less than 50% efficient at collecting solar energy and turning that into liquid carbon, which in turn becomes things that we can sell. So we have to have more plants out there growing more of the time to capture more of that solar energy, and that's where cover crops come in. That's where we can bring cattle in to utilize some of that cover crops and turn it into cash. But when we have more plants growing more of the time, we'll capture more of that solar energy. And then when we do that, we can turn that into capital investments of this organic matter. And when we build our organic matter levels, we don't want to come in and do something like this if we don't have to, where we're taking our residue off or we're doing tillage, because that is like selling off the investments that we just made, and we wouldn't want to do that. Number 5, take advantage of all these free tiny workers. They manufacture, they mine, they transport, they communicate, they protect, they do wonderful things for us. All you have to do is feed them, give them the carbon and let them go to work. Give them a place to live and watch them do their thing. So we want to strive for biological diversity within our systems. Number 6, build and do not destroy your infrastructure, and you'll really see your economy grow. Do what you can to increase the amounts of mycorrhiza, the amounts of earthworms. When you build these infrastructures, things will really start happening. And then when you get that infrastructure built, don't come in and do something like this, because like I said before, that's declaring war on your soil when you try to destroy your infrastructure. Number 7, protect your economy with soil armor. I talked about this before, about how very critical it is to keep the soil covered. It protects it. It keeps it from getting too hot. It helps more rain get into the soil, and it keeps it where it belongs. And then lastly, diversity is so very important for a healthy economy. Plants, roots, and soil animals. We need to get all these things back working into the system. So that's Carbonomics. Like I say, a ton of information. but that's how the soil is working. That's what's going on in the soil. If you have any questions so that we don't get answered here, or if you're watching this recording and you don't have a chance to ask, feel free to send me an email, keith@greencoverseed.com. Also, we have a really good soil health education and resource guide. This actually is the one from a year ago. We've got a newer version. It's 72 pages. It's full color. It's got great articles in here. We would be glad to send free copies out to anybody that wants them. Just shoot me an email and ask for it, and we'd be happy to send out free copies to you for that. So that's Carbonomics. Do we have any questions? You can just type them in the chat bar. I think I'll be able to see the chat bar now if anybody has questions. Eric can pass them on to me as well. I know I'm kind of long, sorry.
There's currently no questions, but if anyone does have a question, you can put it in the chat bar or the Q&A section.
Well, if not, yeah, thanks everyone for attending. Hopefully we get a bunch of people to watch the recording of this later. And like I said, there's a ton of information here, so it may take you a little while to digest it. Don't be afraid to send me an email if you want one of those resource guides that will explain some of these concepts even better.
All right, thank you very much, Keith. Thank you everyone for attending, and hopefully you all have a good night and week.